Hello, I'm Bill Lundgren from Gedae. In this video I'm going to demonstrate how to parallelize a function to run on a multi-core processor. I'm going to use as the target a TI C6678 and 8-core DSP processor. In the first phase of the demonstration we're going to understand the application, and so I had a command that was typed into the command prompt, and I just hit enter to start Gedae so that we can see the application and understand it. The application you can see here by the names is located in the Gedae directory, users Bill J, and the name of the file is runPulseCompression.fg. It's a flow graph. So in the Gedae editor you can either have an application which is entered as a block diagram or a flow graph, or you can have an application that's entered as text. If it's entered as text, when you open it in the Gedae development environment, you'll see a graphical version of the text. This is the application, this is the code that defines the parallelization strategy, but before we consider that, let's open the pulse compression function that we're parallelizing in the editor. Now what I'm going to do is increase the size of the font here so that it's a little easier to read. The main thing to note here is X is the input and chirp is also an input. They're both vectors, and that the return Y is also a vector. So this function is a vector operation, and that's key to how we implement the parallelization. It's key to our parallelization strategy. So now let's take and look at the actual code that describes a parallelization strategy, and we'll open it in a text editor so that it's easier to read. And here again I'm going to increase the font size. So now our input, our data input is complex data, and it's an array. We have two sets of indices. That indicates it's a two-dimensional array, so it's a matrix. We have the chirp that we've passed in. We're going to pass that on into the pulse compression, and we also have a constant which is a number of procs, and that's going to tell us how much parallelization we're going to have. In this case we have set the number of procs explicitly to 8. We could have made that unset and therefore been able to set it via the Gedae tools, but in this case we've hardwired the size of 8 into the application. Let me explain very briefly the parallelization strategy. We have an array with 2 dimensions, and we're doing row operations. So what we want to do is keep the rows intact. We want to divide along the number of rows, so along the columns is how we're going to divide it. In order to do that, we use an rpartFam in order to create subarrays of the original array. Notice that R is the dimension on the original, but R1, which is different. In fact, it will be approximately, and in this case exactly, equal to R divided by number of procs, where number of procs is the size of the family. So effectively what we're doing is creating 8 subarrays of data with the complete rows in each one of the subarrays that can be operated on. The second step is to convert each one of those subarrays into a stream of vectors. So the square brackets indicate array indices, the parens indicate a stream index. So now we have a stream index with R1 vectors in each one of the 8 streams that we have in this example. Now that we have vectors, we can pass those vectors to our pulse compression function, which operates on vectors and returns a vector, so we have a single dimension here. And then we're going to take our stream of vectors that have been returned and recreate a submatrix, and then we're going to take that family of submatrices and we're going to recreate the full matrix by concatenating those submatrices. So that's the parallelization strategy, and that's the parallelization strategy. And the next phase, we will look at how to run that in parallel on a TI multicore DSP. In order to implement this on the target processor, which we've said is going to be the TI multicore DSP, we will open the implementation control, and this gives us the central location where we can make all the implementation settings. The first thing is to tell the compiler where to put the command program, the host for the command program, and here I'm going to enter into this 0, and so this is core 0. We've numbered the cores 0 through 7. Now what I can do is toggle this button so that the compiler will build, not just run on a local processor, but build the application for the target system. The third thing that I have to do is to partition the functionality, and this is called the partition table, not surprisingly. And we just name each of the partitions, and those are ASCII strings, so I use P0 here to put the source on in that partition. And then I'll also put the R part there. And now we have a family. Notice that we have the x2.mv, but there are numbered 0 through 7. That's 8 of them, and we're going to put 1 on each of our processing cores. So we'll put those into partitions using the equation capability for setting these, and this 0 through 7 is can be referred to as $1 in the equation. And so now we've got P0 through P7. Then I'll just copy that equation and I'll paste it in to these Y2 and Y1. Just for completeness, if I open up Y2, we see that's the pulse compression, and so I have 8 sets of functions that are doing the pulse compression. I'm going to be running 1 on each of the cores. So finally, these trailing I'll put in P7. There's nothing magical about P7. I could put it in any of the other processing cores, but I'm just putting them in P7. So now I've broken all the functionality up to go onto 8 processing cores. And the next step is to take those partitions and map those partitions to processors. As I said, I've numbered the processors P0 through 0 through 7, so I'm going to take the partitions P0 through P7 and put them with a $1 onto those processors. I had 2 equal signs there. Okay, so this is going to go on processors 0 through 7. It happens that processor 0 is the host, and so it indicates that. The only other thing I'll do is to map all the memory entries for the trace, because this is my information that records the execution trace. I'm going to map those all to DDR because I want to put that in system memory. I don't want those trace events cluttering up what's in the local memory. So that's all I have to do in order to run the application, and I will hit the run button on the command program. I could have also done that from the control menu. Let me pop this down for the moment. And so what's happening is Gedae is going off and doing its compilation. It links first, and then it figures out all the things that it needs to do in order to implement the application and distribute it, including any data transfers, IPC. In this case, it's all shared memory, so it's primarily doing the concurrency control to avoid using bad data or trampling on good data. And so that's off building that, and it takes a couple of minutes for it to complete the compilation. And what we're going to do is, once the compilation is complete, a message is going to come up, and I'm going to turn on the TI EVM board, and the TI EVM board is going to load a utility which will come back to my computer using FTP. So we're there now. I'll start the board running. So it's actually going to come back to my computer and find the code that was created, and so there it is, and this actually tells you where it found the code, the location of that. So now it downloaded that code and started it running. So we just want to look at the trace, and notice we have the trace enabled, so we'll stop the application and bring up the trace table, and there we have the application running in parallel. This time down here is the source where it's creating the simulated data. So what I'm going to do is zoom in on one of these, and so there we have it zoomed in, and you can see that we are running on partitions P0 through P7, so cores 0 through 7, and that we have above this we have all the trace events that show what's happening in summary on each of the processors, and down below we have the information that shows the details. And in particular, I'm interested in the pulse compression, and I will show you something here. By right-clicking on this, I can bring up statistics for that event, and you'll see that this time is 57.8 microseconds, which is actually fairly slow per FFT that it's doing. You'll also notice that this fire here, 128, it's running at a granularity of 128, so it's actually doing 128 FFTs on the data, and all the data comes from DDR into L2 cache and then back out to DDR, and then it's doing the vector multiply the same way, and then it's doing the inverse FFT the same way. And the next phase, we'll see how we can improve the performance of the individual FFTs by making better use of the cache and by transferring smaller amounts of data. The next thing that we'll do in the demonstration is to again use the implementation control to deal with the issue that we're processing 128 vectors at a time on each of the processing cores, and that data is going into L2 cache from DDR, and then it's going back out again and going back in for the second one and back out. So there is a technique that's commonly called, has been historically called strip mining, and instead of processing, and this is a granularity table, so it shows how many operations are being done during one pass through the application for each of these portions of the application. And so if I open this, if I look at this, we can see that this is indeed the pulse compression that's being done, and there's 128 FFTs and 128 vector multiplies and then 128 inverse FFTs. So in order to make this run faster, what we're going to do is process one vector at a time. So I'm just going to set all of these to 1, and we'll leave everything else the same. Notice the asterisk indicates that I've modified the default settings. What I'm going to do is to save the group settings, and so it saved them into this demo 1. And so that's all I need to do in order to see if I can improve the performance. And so I hit the run button, and again we're going through the compilation process with the compiler. During the video we'll actually jump ahead here a little bit so you don't have to watch the compilation process again. Okay, so now it's waiting for us to turn the processor on so that it can run the bootloader and download the code to the TI processor and start it running. I wasn't quite quick enough on the draw of getting it started, so it's still waiting for the EVM board to download. So it's downloaded and started it. We don't need it to run very long. We'll stop the application. Once again, we'll bring up the trace table, and we want to see if there's a difference. It turns out that the time was around 22 milliseconds for running the complete application, and what we see here is if we measure this and zoom in on it, that the time is now around 16 milliseconds. So we've actually been able to cut off in the neighborhood of 6 milliseconds out of 22, so over 25% increase. Once again, if we look at the processing, now you see that we're 128 times doing an FFT, a vector multiply, and then an inverse FFT. And again, we can look at the function and see what the timing is for it. It's now running in 47.5 milliseconds, so we've improved by over 10 microseconds each one of the executions, each one of the firings, each one of the FFTs that's processing a single vector. So we have gotten an improvement, but the question is 47.5 particularly good? And it turns out that if we look at the inverse FFT, we see that the time there is still 59.5, and so there is room to actually improve this, because we know that the 2048 point FFT can run faster than this. So what I'm going to do is go to the next phase, and I'm going to try and increase the size of the granularity from 1 to a larger number and see if that improves my performance. In this phase of the optimization, we're going to increase the granularity of the firing and the fire table. As you recall, our granularity was equal to 1, and we want to see if we increase that so it better fits into or it's more suitable for L2 cache size if we actually get a better performance. So I'm going to change all of these from 1 to 4, and so instead of firing 128 times with a granularity of 1, it's going to fire 32 times with a granularity of 4. So we simply make that change, and we'll save the group settings, and then what we'll do is run the application. Once again, we'll jump forward to avoid having you watch the compilation. And there it's running the application. Once again, we can stop it. We don't need a lot to run it for very long. So it stopped, and we can bring up the trace table, and again we'll zoom in on one of the sets of events, and we'll see how much time is involved in the actual execution. Well, there's a couple things. Is that we can see that the bulk of the events are around 11 milliseconds, so we've dropped from 16 to 11, a decrease of 5, so over another 25% decrease in the processing time. We do note that P0, which is running on core 0, it actually appears to be taking longer than the others, and we'll investigate that in a moment. Let's look at the times for these, and if this is P1, and so we see that the fire time is 42.743 microseconds. We see the time for the vector multiply is 8.4 microseconds, and for the inverse FFT it's 32 microseconds. And so those are good times, but if we go back to P0, we can see it's noticeably longer. And one of the things that we notice right off is that the vector multiply seems to be longer. Let's see what the times are. This is 37.938. That's actually faster than P1. If we look at the vector multiply, that's 25 milliseconds versus 8.4 microseconds, so that's a lot slower. And finally, the inverse FFT, we see it's 32, so that's about the same. So we've got an issue here that the that the vector multiply in particular is running slower on P0, and we know the reason for that is because P0's default memory is DDR, whereas P1 or core 1 through core 7, the default memory is MSM. And so we're going to fix that. We will do that in the next phase of the demonstration. In the next phase of the demonstration, we're going to deal with the issue of the events on P0 running slower than on the other cores, P1 through P7. To do that, what we're going to do is bring up the schedule parameters, and this is a table that gives us information about the threads that are running on each of the partitions on each of the processing cores. The one we're interested in is P0, and you can see that we are actually running this thread out of default memory, which on core 0 is the DDR memory. And if we open that thread up to see what's actually in the thread, you'll see that it is the pulse compression that's running there. And what we want to do is, instead of having that in DDR, that's the default memory, we basically want to put it in MSM memory. And so we can override the default and put it in MSM memory. So the next thing that we do is to actually go back and run the application, and of course it compiles. And at this point we're going to pause and restart after the compilation is complete. Okay, now the compilation is complete, and we're going to start up the EVM board and wait for the application, the code, to be downloaded. We see it's being downloaded, and it will reset and start running the application. And we'll stop it and bring up the trace table so that we can see what's actually happening on the processing cores. What we see is that now core 0 is aligned. The green indicates the end of the processing, and that's aligned with everything else, and we're running at around 11 milliseconds for the total time. So the last thing to do here is to actually check the times and see on P0. We want to see on this one what the times look like, and we have a time of 42 milliseconds, a time of 9 microseconds, microseconds, and 32. So this is in line with what's going on in the other processors. There are additional optimizations that require updating the board support package for the TI processor, and I'll talk about those. So the question is there additional optimization we can do? And the answer is yes. We have not yet implemented in the BSP manual multi-buffering of data from DDR into the L2 cache. That's something that we plan to do, but we haven't yet done it. And when that's done, we would expect the timing of these FFTs, both the input and the output timings, to improve, because the transfers from DDR into L2 cache and the transfers back out from L2 cache to DDR will be running in parallel with the processing that's going on. At the moment, this is relying on the hardware cache management to do that, and there are some inefficiencies associated with that hardware cache management. So the thing that you should take away from this video demonstration is that you can take an application and a function, in this case pulse compression, and in a small amount of time, an hour or 2 hours, you can establish a parallelization strategy for that. You can map it to a target processor. You can optimize it for that processor by tweaking the implementation settings, and end up with an implementation that is better than what you'll get from a hand-optimized version, or at least as good as what you'll get from a hand-optimized version of the application. Thank you very much for listening.